In this Introduction to Stochastic Models video, I'm going to talk a little bit about different kinds of stochastic models and different kinds of stochasticity and what they mean, particularly in terms of population models. First, let's quickly get straight the difference between deterministic models and stochastic models. In a deterministic model, everything in the model is determined from the beginning. Every time you run the model, it'll come up with the same results. Let's say I have my deterministic population growth model, n at times t plus 1 is equal to n at times t times some growth rate lambda. This is a deterministic model because if I know what lambda is, and I know n at time any t really, because if I know lambda and n at times t, it tells me all of the possible n at t's into the future, and I can extrapolate backwards in time as far as I want, forever. The whole process is determined. A simpler way of thinking of deterministic models is that nothing in them is random. Right, so that's a pretty standard deterministic population growth model. A stochastic model is any model that has some element of randomness to it. Every time you run a simulation of the model, it will come out different because somewhere in there is a random process. For example, the stochastic equivalent of this model would be to say n at times t plus 1 is equal to n at times t times lambda t, the growth rate at times t, where lambda at time t is drawn from some distribution, some random, well, not some random, but some probability distribution every time t. So we'll say lambda, in this case, we'll just make it normally distributed with a mean of, I don't know, 1.2 and a variance, say, 0.02. So it's small. There's not a lot of noise, but it's some noise. So what does it matter if we add randomness to our models? Well, just for a quick comparison, if I actually ran models like this, a deterministic exponential growth model and a slightly stochastic one, what you'd see is that for any initial population size n, the deterministic model, lambda is 1.2, so it's going to grow pretty quickly and exponentially. So that's my deterministic model. If I use the stochastic model, every time step, my population is going to grow on average at a rate 1.2, but not always exactly 1.2. So sometimes it'll grow, sometimes it'll shrink, and you get a little bit of noise. And because I set the variance to not be very big, right, most of the time you'll get trajectories that are pretty close to the deterministic case. But in any stochastic model, even if the variance is small, it's always possible for weird things to happen, like population extinction. You just might get a bad run. Or you might get a huge population explosion. A fairly unlikely event, but still possible. So stochastic models let us ask all kinds of interesting questions about our system that deterministic models don't allow. Like, interesting stuff happens, like, what's the probability of extinction in a population with these growth parameters? Or what's the probability of extinction in the next 100 years? Before the year 2100. Or what's the probability that n is going to be greater than 1 million by the year 2100? In a deterministic model, I can tell you what my population size will be at any given time, but that's all really. Because there's no allowing for the kind of random events that are really a feature of every biological process ever. So there's a fairly solid argument, I think, as a biased person who makes stochastic models for a living, that if you're going to model a biological process, particularly population processes, the best model, or the most useful model and the most interesting model is usually going to be a stochastic one. Unfortunately, they also tend to be a little bit more complicated to analyze. So it goes. The other thing I want to point out is that most of the time for stochastic models, depending on the probability distributions you're using, you need to know both the mean and the variance of the randomness you're adding into your system. Particularly the variance matters, because if the variance is large, then your trajectories have more wobbles in them. And one other diagnostic difference between deterministic and stochastic models is that the endpoint of a deterministic model is just that, a single endpoint. Whereas for a stochastic model, your end result is going to be a distribution of possible endpoints. So if I want to know what's going to happen to my model, this one, what's going to happen at n at times t is 100, instead of just getting a value, I'll get a distribution of possible values. Or a distribution of possible outcomes, I should say. So most of what we do when we make stochastic models is analyze those distributions of possible outcomes. In a stochastic population model, there are typically two sources of stochasticity: demographic stochasticity and environmental stochasticity. And I'm going to talk about each of those just for a couple. They're just different ways of putting randomness into your model. Demographic stochasticity is the random change in population size due to random fluctuations in birth or death rate, or rather, random fluctuations in demographic parameters. So demographic parameters are birth rate, death rate, immigration, and emigration. So thinking back to the simple stochastic model of exponential growth, n at times t plus 1 is lambda t times n at t. Remember that growth rate is really births minus deaths. So if I want to include demographic stochasticity in my model, I can make my birth rate stochastic, I can make my death rate stochastic, or I can make both of them stochastic. So if you're actually simulating a stochastic model like this, what you would do would be every time step, draw your birth rate and or your death rate from some probability distribution, and then plug those in and crank the population forward in time. Right? And if you have a fancier model where the growth rate is birth minus death plus immigration minus emigration, you can make any or all of those stochastic as well. By the same method of drawing a value for them from a probability distribution every time step and using that to project the population forward. This kind of variation is roughly analogous to genetic drift, since it's not biased in one direction or the other. So this kind of stochasticity just makes the population wobble around the expected mean of all of the parameters. I'd also like to point you can have stochastic density dependence. Right? In a density dependent model, n at times t plus 1 is n at times t times some density dependence term, lambda times 1 minus n at t over k, for example. So if you wanted to make a density dependent model stochastic, you'd just take your lambda again and draw it from some distribution where the mean of the distribution is this whole thing, lambda multiplied by some density dependence term. So every time step you actually change the distribution you're drawing from because of the n of t in. But it's still just demographic stochasticity because it's a random change in our demographic parameter lambda. Environmental stochasticity is just what it sounds like. It's fluctuations in population size driven by environmental changes, or environmental factors, I should say. And if we know anything about the environment, it's that it's a random process. So, Environmental stochasticity tends to be more analogous to natural selection in the sense that you maybe have two different environments. Quite often we'll model things such that there are two different environments, one's good and one's bad. So every year the environment puts selection on your system in one direction or the other. So the changes in the environment are kind of analogous to a fluctuating selection model situation. So for example, let's say I'm monitoring my attempts to grow wildflowers in my yard. So I'm keeping track of the population size of poppies. I'm going to divide my environmental states into either wet years or dry years. So my environments, say we've divided everything into wet years and dry years. And on wet years, I'm going to call wet years good years. And in good years, the growth rate is greater than 1. And in dry years, which are bad, growth rate is going to be less than 1. So depending on the sequence of environments my population sees, it might grow or shrink depending on how many of those years are good or bad and the order in which those occur. So my model would still look like n at times t plus 1 is n at times t times lambda t. But now, lambda is a function of environment at time t. If the environment at time t is good, lambda at t is going to be, or if the environment at times t is bad, lambda at time t will be less than 1. So this defines the stochasticity of my, and we might say that wet years are Poisson distributed. So there's some given probability, right? Every year we define P good year as 0.7 and P bad would then be 0.3. So I could use a Poisson process to model my environment and then use that to update my population size. So in practice, if you're making this kind of model, you start with your initial population size and decide what the distribution of environments will be. And then for each time step, you draw an environment out of the random process and then use that environment to choose your growth and update the number of individuals. The next year, you draw another environment, which tells you your growth rate, and you can update the population size. Rinse and repeat for as many years as you want. And then do a number of those simulations to get a distribution of the outcomes. It's also entirely possible to have both environmental stochasticity and demographic stochasticity in your model, just like it's quite possible to have a genetic model that has both selection and drift. A little bit about Markov models and Markov chains. All the models I've talked about so far have been Markov models, because the defining property of a Markov model is the Markov property. Markov property is that the future in your model is defined entirely by the present. Having additional information about the past doesn't help you. Which basically just means that n at times t plus 1 is a function of n at times t, right? And only n at times t. If I knew n at times t minus 1, that would give me no information about what's going to happen at nt plus 1. The future state depends only on the present. You can have continuous time Markov processes as well, but the Markov property still holds, is that for any time point in the model, the future is uniquely defined by the past. The future is uniquely defined by the present. These processes are also referred to as being memoryless, in the sense that is whatever happened in the time step before the one you're looking at becomes irrelevant as you try and go forward another step. There's going to be a whole section devoted to Markov models, so I'm just mentioning their existence right now. Another kind of stochastic model you hear talked about is a random walk model, which is an awful lot like what it sounds like. Random walk is a random process model where every time step, the process moves some distance, takes a step that has some distance and some direction. and both the step length and its step distance can be random variables. The simplest random walk is a one-dimensional random walk. So we'll walk along the number line. So here's my number line, here's 0. 1, 2, 3, 4, -2, -3. So in a one-dimensional random walk, the process starts at 0. Every time point you flip a coin, and if it's heads, I go to the right 1 step, and if it's tails, I go to the left 1 step. That's a simple random walk. And as I flip coins, I'll go right 1 step sometimes, I'll go right again, then I'll go back, then I'll go that way, and then maybe I'll go that way, and then maybe I'll get some more tails. And the process will move around randomly. A lot like again, a lot like genetic drift. In fact, one of my favorite random walk models is the Wright-Fisher model of random drift. If you want to model the genetic drift in your population, you start at some allele frequency p, and every time step, the allele frequency changes, basically goes on a random walk. So this drift model is actually both a random walk and a Markov chain. These are both one-dimensional random walks, but you can use multi-dimensional random walks where your directions go beyond up and down, they could be left and right, to model things like foraging behavior and animal movement across a landscape. In order to model a random walk for every time step, right, for each time step of a random walk, you need to choose step length, how far you're going to go on your random walk, and the direction. Are you going to be going, in my one-dimensional random walk, am I going to be going right or left? In a more complicated random walk model, step direction might actually be north, south, east, west, or something fancy like that. So now that we've learned some of the vocabulary of stochastic models and about different kinds of stochasticity, in the homework, you're going to actually go build some of these models and play with them and get a feel for how they behave and how the different kinds of stochasticity change the outcomes of your models.